Hello everybody, it's Mrs. Pound and I'm back with another video from Chapter 7 on chemical bonds from BJU Chemistry's 5th edition. We're going to work on the second part of section 7.2 on ionic bonding and metallic bonding. So our objectives today will be to compare covalent ionic and metallic bonds and predict the type of bond that will form between two atoms when given their location on the periodic table. So for ionic bonding, this is between a metal and a nonmetal, two elements like sodium and chlorine. The metal, which is sodium, loses electrons to become a sodium ion, Na positive, and the nonmetal, chlorine, steals electrons to become more negative, to become an anion, Cl negative. What holds the bond together is attraction between oppositely charged ions, the sodium ion and the chloride ion. And with these type of bonds, ionic bonds, there is a large electronegativity difference. The closer to the number 4, the more ionic it is. And we can see here, we subtract the electronegativity. So chloride ion, or chlorine itself, has an electronegativity of 3.2, sodium 0.9. We subtract to get 2.3. And like I said, the closer this gets to 4, the more ionic the bond. The structure of ionic compounds. Chemical compounds formed from metals and nonmetals are called ionic compounds. So sodium chloride is an ionic compound. They do not form distinct molecules like covalent compounds, so it is inappropriate actually to call them molecules. Instead, we express them as a formula unit. A formula unit is an expression of the ratio of cations to anions in an ionic compound. This is different than writing the molecular formula because the molecular formula is actually the formula for an actual particle, not for a ratio, even though they look pretty much the same. And an example is table salt, and I'm going to show you how we get the formula unit from the Lewis structures. For the formula unit for sodium chloride or table salt, what we do is we first write the Lewis or dot structure for sodium. So sodium has one valence electron, so we'll give that one valence electron. There's sodium's one valence electron. So it has one electron to give up. Chlorine, if we put a chlorine over here, it has this structure. It has 7 valence electrons, so it needs 1 electron. So what will happen is this 1 electron will join this one here, and we will then write the Lewis structure like this. So Na positive because it lost its electron, and then chlorine like this, and I'm going to put that there, will be negative. So the formula unit for sodium chloride is simply NaCl, 1 sodium for every chlorine. Let's do another example, calcium fluoride. And again, I'm going to show you how to figure out the formula unit using Lewis structures. The formula unit for calcium fluoride is a little bit trickier, but not too much. So if we write down the electron dot notation for calcium with Ca, it has 2 valence electrons because it is in group 2. So it wants to give up 2 electrons. Now, fluorine is in group 17, so it has 7 valence electrons, and we see that it can take 1. But there are 2 over here, so what we do is we simply add another fluorine. And now both of these electrons can bond. And so we write this like this. So Ca, it lost 2 electrons, so it's 2 positive. And then we have 2 fluorines. So F and another one. So when we write this formula unit, it's CaF2. So that's how we figure out the formula unit using Lewis structures for ionic compounds. Now, these formula units, because they're a ratio, these ionic compounds form what's called a crystal lattice. So they tend to be crystalline compounds, and a crystal lattice is an orderly arrangement of ions in a 3-dimensional pattern within a compound. Much like this pattern on this lawn here, except for it would be 3-dimensional, not just flat 2-dimensional, but a regular pattern like in the background. And I'm going to show you that for sodium chloride. The lattice structure for sodium chloride would look like this. So you would have a positive sodium, a negative chloride ion. And you would keep just alternating these because it's a 1-to-1 ratio, like this. Now realize this is 2-dimensional, so this would be also going back into the page, and next to each sodium would be a chloride going back, and then another sodium and another chloride. So this would be 3-dimensional, but in a nice geometric shape. That's why when we see sodium chloride crystals, they are in cubes because of their structure here, their lattice structure. It forms a cube. For metallic bonding, what we have is we have the positive nuclei of the metals in a crystal type structure. So I'll do this. And then around them in an electron sea or cloud are the electrons. So this is the electron cloud. And that electron cloud will have all kinds of negative charges in it. Now, we also have what are called polyatomic ions. This is a charged group of covalently bonded atoms that often act as single charged particles in chemical reactions and solutions. Some examples, and there are lots of them on table E, which we're going to take a look at in a minute, are hydroxide, which is OH negative, which we'll become very familiar with. Some examples of polyatomic ions, which there are a lot of them in table E, which we're going to take a look at in a minute, are hydroxide ion, OH negative. The oxygen and hydrogen are covalently bonded, but as a unit, they act as an anion. And ammonium ion, NH4 positive. Again, the nitrogen and the hydrogens are covalently bonded, but it acts as a cation when interacting with other elements. So in table E, we see here a number of polyatomic ions. Some of the ones that we are going to use the most are hydroxide, ammonium, which I already mentioned, nitrite and nitrate, sulfite and sulfate are also very common ones we use, and permanganate, carbonate. So these are all, when you see these groupings, these are polyatomic ions. Now let's talk about metallic bonding. Most metals are likely to freely share electrons when bonding with each other because they have low electronegativities and low first ionization energies. So they don't have much of an attraction for the electrons, and they give them up very easily. What we have developed is the electron C model. This is a model for explaining bonding in metals and the properties of metals that states that metals consist of an extensive crystal lattice of metal cations surrounded by and submerged in a sea of mobile electrons. So the electrons can just go everywhere, but there is a definite structure to the nucleus of the atoms, that they're in a fixed spot. And I'll show you an example of that here. The electron C model accounts for the metallic properties of luster, conductivity, and ductility. It's due to the fact that the electrons are mobile, that metals are so shiny that the electrons move and can conduct electricity, and that the metals can be drawn out into wires. Now, delocalized electrons are mobile valence electrons in a metallic bond. This is how they are described. They don't belong to any locality, any particular location, so they're said to be delocalized. So our objectives today were to compare covalent, ionic, and metallic bonds and predict the type of bond that will form between two atoms when given their location on the periodic table. So don't forget your 5 questions in your notes.